In this video, we're going to take a look at an application of the derivative known as related rates. Now, what is related rates all about? Well, it has the word rate in there, so our main focus is going to be computing the rate at which a variable might be changing, but that variable won't be given as a function of time, but instead it will be given as a relation with other variables, right? So I know that sounds a little strange, but let's take a look at this example. So suppose that y and x are differentiable functions, but of t, so differentiable functions of t, right, and are related by the equation, and I'll choose a pretty simple equation to describe this relationship. So let's say the equation is y equals x squared, or basic parabola, right? So before we were just saying that y is dependent on x, but now we're saying that both of these variables are functions of time. So it's like your x variable is changing over time and your y variable is changing over time, but they are also related by this single equation. And there's a way you can sort of visualize what this is all saying. If we sketch our parabola, right, and think of this parabola as a road, and we have an object on this road, and you have a slider that controls the x values, right? And what you're doing is you're moving that slider, let's say, at different rates. So at sometimes, you're moving it very quickly, other times you're moving it slowly, and as you do that, you cause the object to move along this parabola. So it's like it's stuck in a groove, right? This parabolic groove. And for instance, you might be changing the x variable at a certain rate, and you might be then asking your question, at what rate does the y variable change? Or it could be flipped around. There could be a slider where you change the y, and again, changing the y would cause the object to move along the parabola. But as it moves, then it has to move with some rate of change. As long as an object is moving, right, then it's going to have some rate of change. So the idea is you're going to have an equation, or we might have to derive the equation that relates one, or let's say two or more variables, and we might know the rate of change of one of these variables, and we're asked to find the rate of change of the other variable at a specific instant, right? So before I give some numbers here to do a brief example of this. Now, the idea that both x and y are functions of t, it means I can write the equation like this, right? So x of t squared, right? It's still telling me the same relationship. I'm just making it now very clear that x and y are functions of t, right? Now, if that's the case, then if I'm going to differentiate this equation, I would differentiate it with respect to t. Like if I want to find the rates, right? So I would differentiate this side with respect to t and this side with respect to t. So let's write that down. So differentiating both sides with respect to t, well, this is what we will get. Well, if I differentiate this side with respect to t, I'm going to get dy dt. If I differentiate this side with respect to t, I'm now going to have to use my chain rule because I have my x function, but then it's being squared. So using the chain rule on this side, I have to bring the 2 down, and then I have to keep the x of t and then I have to subtract 1 from the power, and then I have to multiply by the derivative of the inside with respect to t. So dx dt. So now this new equation, right? In fact, let me write this down. So dy dt is equal to 2 times x times dx dt. So whereas this equation just gives me the relationship between the two variables, this equation now gives me the relationship between the rate of change of y, the x variable, and the rate of change of x, right? And therefore I can use this equation, like if I'm given one of these rates of change, I can then solve for the other one, all right? So let's do a couple examples just with this equation here. So let's say we're at a specific point on the parabola. So at the point, now I just have to make sure that whatever point I pick is a point on the parabola. And the easiest way to do that is if I pick my x, let's say I pick -3, if I square -3, I'll get a +9. So I know that this point is some point on my parabola. So at this point, let's say if dx dt is equal to -2, right? What is dy dt, right? So if x is changing at a rate of -2 units per unit of time, right? At what rate is the y variable changing? Well, I mean, I have all the information I need. I know the x value, I know the rate of change of the x value, and then I can plug those two numbers in here, and then that will give me the rate of change of the y variable, right? So dy dt would be equal to 2 times the x variable, so that's -3, times the rate of change of the x variable, which is -2, and then this gives me, so 2 times -3, that's -6 times -2, so a +12, right? So what this all is saying, let's write a sentence that actually summarizes what all these numbers mean. So at this point, right, so at the point -3, 9 on the parabola, if your x coordinate is decreasing at a rate of, so let's write that down, if so if the x coordinate, right, is decreasing, and we know it's decreasing because it's a negative rate of change, so is decreasing at a rate of, so it would be -2, or it would be decreasing at a rate of 2 units of x per unit of time, so unit of t. So if, again, we're on this parabola at this specific point and our x coordinate is decreasing at a rate of 2 units of x per unit of y, then what did we just show? We showed that the y variable will be increasing at a rate of 12 units of y per unit of t. So then the y coordinate is increasing at a rate of 12 units of y per unit of time. So units of y per unit of time. So if we were at a different point, we would likely have a different rate. And also, if x was changing at a different rate, that would also affect the rate of change of y. So there are two things now affecting the rate of change of y. It would be the x coordinate and the rate of change of that x coordinate. All right? Now, let's do another example where the relationship is a little more complicated, right? So let's say it's something like, so here's another example. So I'm just going to write down the relationship. So let's say x squared minus xy plus 5y. And let's say this is equal to 5, right? And we know that, so here is the point, 1 comma 1, right? So here's the relationship between our variables. This is the point at which we are on this curve. And suppose I know that dx dt, let's say, is 1/2, right? The question is, what is dy dt? So what is this rate of change, right? So again, in a problem like this, in a very basic scenario, you're going to be given an equation. It could be explicit like the one we just did with the y equals x squared, or it could be implicit like this. You'll be given a point which kind of represents an instant. So, at the instant where x is equal to 1 and y is equal to 1, if we know that the rate of change of x is 1/2, what is the rate of change of y? All right? Well, when information like this is given, what it now implies is that x is a function of t and y is a function of t. So we can rewrite this equation to express that fact, right? So we could do this, very similar to what we did with our implicit equations. But now these equations involve a third variable, if you will, the time variable, right? So I'm basically writing all our variables as functions of t. Right? So the only thing that's not a function of t is the constant, right? Okay, so then once we kind of have this conceptual thought going through our minds, then let's differentiate with respect to t. So differentiate term by term, but now with respect to t. So with respect to t, right? Let's see what we get. Well, for this one, I need the chain rule. So bring down the 2, keep the x of t, and then subtract 1 from the power, and then I have to multiply by the derivative of the inside. So there I'll get dx dt. Now here I have a x function times a y function. So because it's a product, I have to do my product rule. So I'm going to put the minus there, and then I'm going to open parentheses because I know the product rule has two terms, and I want to make sure that I distribute this negative correctly to both of those terms. So doing a product rule, the derivative of this function with respect to t will be dx dt, and then times the second, so y of t, and then plus the first, so that's x of t, times the derivative of the second, which gives me dy dt, right? So that's from our product rule, and then plus, and then use our constant multiple here, bring the 5 down and multiply, and the derivative of y with respect to t will be dy dt. And then as usual, if we have just a constant on this side, then the derivative of that constant is going to be 0, right? As I said, this is the only thing that does not depend on t, all right? Okay, so now again, this equation gives us the relationship that we need. But now let's write it without the of t. So let's drop all the t's and the parentheses. So it looks like this: 2x dx dt minus, and distribute that negative sign, dx dt times y of t, and then, or well, actually just minus y, since I'm dropping the of t. And also this negative will change that plus sign to a minus, and then I have x dy dt, and then plus 5 dy dt, and then that's equal to 0. All right. So this equation, it gives me the relationship between or amongst four things. Because notice, my x variable is still there, my y variable is still there, and now I have this rate of change of x and then this rate of change of y. And this equation gives me the relationship between all four quantities, right? The two variables and the two rates. But since we're asked to find dy dt, right, I know what x is, right? X is so at this instant, let's write this down. So at this instant, x is equal to 1. That's here. Y is equal to 1, right? We get that from our ordered pair. And we know that dx dt is 1/2. So then I can substitute all the information I know in this equation, and then hopefully I can solve for dy dt. So let's plug in what we know. So wherever there's an x, put a 1. Wherever there's a dx dt, put a 1/2. Right, and keep going. And then minus, here's another dx dt, so that's 1/2. And then times y, that's 1. And then minus x is 1. Now I don't know what dy dt is, so I'm going to bring that down. So that's going to be my only unknown in this equation. And then similarly, bring down the 5 dy dt, and that's equal to 0. So now if I can solve this equation for dy dt, right, then I'll have my missing rate of change. So let's see what we have here. This is 1, and then this is minus 1/2. Now I have a negative 1 dy dt plus 5 dy dt. Probably the easiest way to think of it this way is to factor out a dy dt. And then in parentheses I would have a negative 1 there and then a plus 5 there. So basically what you're doing is you're adding like terms. You add this coefficient of negative 1 to this coefficient of positive 5, and then you're going to get a coefficient of a positive 4 that's multiplying my dy dt. And then I can simplify these two terms. So 1/2, or 1 minus 1/2, that's 1/2. And then I have that's plus 4 dy dt, and then that's equal to 0. So if I want to solve this for dy dt, subtract 1/2 from both sides. So 4 dy dt is equal to negative 1/2. And then to isolate dy dt, divide both sides by 4. So dy dt is equal to negative 1/2 divided by 4. So the rate of change of y with respect to t at this instant is negative 1/8. Right? And if we had a different instant, then we would have different values for x and y, and then possibly a different rate of change of x, and then that would affect dy dt. Right? Let's do one more example just to kind of wrap this up, and it's kind of a little story problem. And let's see what this one is, right? I mean, there are times when you're not going to be given the direct relationship between the variables. There are times when you might have to figure it out using geometry or maybe using some specific formula. But let's say air is being pumped into a spherical balloon, right, at a rate of, right, so we're told a rate of 3.5 cubic inches per minute, right? So we're inflating this balloon at a rate of 3.5 cubic inches per minute. Then it says find the rate of change. So find the rate of change of the radius of the balloon. Right? So the radius of the balloon when the radius is 3 inches. So when the radius is 3 inches. All right. So we look at this and, we're not given an equation. We're basically given one sentence. We're told that air is being pumped into a spherical balloon, so a sphere, at this particular rate. Now, looking at the units, inches cubed or cubic inches, that has to do with volume, right? And then the minute obviously is a measure of time. So this is a rate of change of volume with respect to time, right? So let's write down what's given. We're given that dV dt is equal to 3.5 cubic inches per minute. Again, how do we know it's dV dt? Take a look at the units. So this is where we may have to rely on units to determine what sort of rate is given, right? So again, cubic inches is a measure of volume, and minutes is a measure of time. So that rate is dV dt. So that's given. Also, what's given is the rate of change of, it says find the rate of change of the radius when the radius is 3 inches. So that's when r is 3 inches. And here's what's asked for. So we're asked for, it says the rate of change of radius. So that will be dr dt. So this is the missing rate that we would have to find, right? So again, how do we find this without an equation? Well, what we then have to ask ourselves, what is the relationship between the volume and the radius of a sphere, right? So it comes down to, can we find, or do we know, the relationship between the volume of a sphere and its radius? And we do know. Here is the relationship, right? So the volume of a sphere is 4/3 pi r cubed, right? So if I know the radius, if I cube it and then I multiply by 4/3 pi, that will give me the volume, right? So this is the equation that we need in order to answer this particular problem, right? So there are some questions out there where we will have to make use of formulas from geometry to get the relationship between our variables. Or it could be we have to use principles from trigonometry in order to do this. All right? But what this implies is that v of t, right? So our volume is changing over time. As we inflate this balloon, the volume will change, and so will the radius. So both of those quantities are functions of time, right? So now if I differentiate this equation with respect to t, right? So if I differentiate with respect to t, well, this side will give me dv dt. The 4/3 is a constant multiple, so that comes down. The pi is a constant multiple, so that comes down. And here I will need my chain rule. So bring down the power, so I'll have 3. Then I keep the inner function, which is my r of t, my radius. Subtract 1 from the power, that's what my power rule says to do. And then the chain rule says I have to multiply the inner function, or multiply by the derivative of the inner function. Well, the derivative of r of t is dr dt. So now let's write this equation without the r of t form so we can see it, right? So here is the equation that we're going to work with. So dv dt is equal to, now if you look at it, the 3 reduces, right? So we have 4 pi, then we have a radius squared times the rate of change of our radius, and this is what we want to find. And if you realize we have everything else that we need, we know that the rate of change of volume is 3.5, the radius is 3, and then yeah, we're asked to find this missing rate. So at this instant, right, so at this instant, r is equal to 3. I don't even need the volume at this time, right? I don't need v, I just need to know the radius and the rate of change of the volume, and that's the 3.5. I'll put the units at the very end, right? So substitute what we have. So the 3.5, what I'm going to do, I'm going to write that as a fraction. So this is 7/2. That's 3.5 as a fraction. And then I have the 4 pi times now 3 squared, which is 9. And then here is the rate that I'm trying to solve for. So what I have here is 36 pi when I multiply. So 36 pi, so we have 7/2 is equal to 36 pi times dr dt. And then solving for dr dt, that means I have to divide both sides by 36 pi. So then you end up with 7/2 times 36 pi. That's equal to the rate of change that I want, right? And then so the denominator, so what we have, so therefore dr dt at this instant is 7 over, now 2 times 36, so that's 72. So we have 7/72 pi. And then the units now, think about what the units of radius would be. Well, that would just be inches, right? If the volume is in cubic inches, then the radius is just in inches, and then it will be per unit of time, which in this case is per minute. So that's the rate at which the radius is changing at this particular instant. If we were given a different r value, like when the radius is 4, then we would end up with a different rate of change. It just shows you how this concept of an instantaneous rate of change really plays out, right? Because it depends on what value of r you plug in. In this case, it looks like if your r is small, right? So if r is small, like 0.01 or zero point 0.1, then your rate of change is going to be big because you're going to be dividing by a very small number. And that makes sense. Think about it. When you're inflating a balloon, it tends to expand more rapidly at, at the initial stages of inflation, right? So when you just start to blow it up, it expands more rapidly. But the fuller it gets, it doesn't expand as rapidly anymore. And then if you continue to do it, at some point it's gonna, explode. You're gonna burst, right? So you can actually think about it, and physically these numbers make sense, right? These are not just numbers just pulled out of thin air, just for the sake of making up a problem, but they tend to reflect what we observe in reality, right? So that's the concept of related rates. Hopefully, you found it interesting and enlightening, and we'll see you in the next video.